Hi guys, it's Kate, and this is a full walkthrough of the Spring 2015 second midterm exam for Math 1B. Let's get started. We begin with a typical Taylor polynomial problem. We're told that we'd like to approximate the cube root of 8.3 by using an appropriate degree 3 Taylor polynomial for the function cube root of x. And our first question right off the bat is a question that you should ask yourself anytime you're being asked to create a Taylor polynomial. What would be a good center for the approximation and why? The answer to this is that we want to center this approximation at 8. There are two reasons for this. One of them is that 8 is very close to 8.3. The other is that 8 is an input value for which we know the function value, because the cube root of 8 is nice and even. Well, it is even, but also a whole integer, 2. And then the various derivatives are very easy to compute at 8 as well. So not only are the function and its derivatives computable at 8 by hand, but also 8 is close to 8.3. Those are the two answers that you need for part A. Now the second part is really the meat of the question. It's to go about finding the relevant degree 3 Taylor polynomial for the cube root of x, and we want to totally simplify the polynomial's coefficients. Here's a great way to format your work for a problem like this so that graders can very easily follow your work and you won't get quite so confused about anything. In each column, I have individually the particular function or derivative of the function I care about. Then I have that function evaluated at the center, and then I have the relevant coefficient that contains information about that function value or that derivative's value. Since we're going for the degree 3 Taylor polynomial, that means that we need to take x minus c, x minus the center, or x minus 8 in this particular question, all the way up to the third exponent. We want to be able to cube it, which means we need a0, a1, a2, and a3. So we wanted to take up to the third derivative. Let's take a look at what those look like. So here's all the work for finding out what the various coefficients need to be of this Taylor polynomial. This is a great way for graders to find errors in your work if there are any. Without this work shown, it's very difficult to give partial credit if there are mistakes. So be aware that showing your work is a good thing here. Remember that also the difference between the function value and derivatives at the center and the actual coefficients is that the coefficients need to be the kth derivative of the function at the center divided by k factorial. So you'll see that factorial factor in the denominator of a2 as well as of a3. Putting this all together, we're able to write down the relevant degree 3 Taylor polynomial for the cube root of x centered at 8, and we get the following. And there we have it. Remember that we have x minus c, our center being c, which is 8, in each of the terms. We have a0, a1, a2, and a3. And that's our final answer. Part C asks us to use this third degree Taylor polynomial approximation to approximate the cube root of 8.3. All we have to do is plug in 8.3 for x. And here's what we get. If we go about simplifying each of these terms, this will become 1/40th. The third term will become 1 over 2 to the 5th times 10 squared. And the final term, the 3 cubed, will cancel with the 27. The 10 will cancel with one factor of 10. And so we're left with 1 over 2 to the 8th times 3 factorial times 10 squared. Note that that denominator can also be written as 2 to the 9th times 3 times 10 squared as well, but it's up to you. And that's problem 1. Number 2 is one of those infamous series problems, where there are a whole bunch of series, you have to decide whether they converge or diverge, and then you have to choose a rationale as to why they do so. And in this particular example, you can only use each rationale at most once. Sometimes next to the rationales down at the bottom of the page, there's a little bit of an explanation that you need to provide, but otherwise, that's really it. Let's get started. How do you tackle these? How do you think through them? You want to go one at a time. As I read over these, it's really easy to get overwhelmed. And the first thing that I want to do is just calm down. don't spend too long on any one series, but also don't jump between the series without allowing yourself to draw conclusions about them. As I look at these, I sort of notice the fact that there aren't a ton of alternating series. I mean, right off the bat, this is not an alternating series. This is not an alternating series. These two seem to be alternating series, and so as I look at them, well, I take a look at this and I think to myself, that seems like it could be ripe for the alternating series test. So let's start with that third series. The alternating series test means that it is an alternating series, which is true, right? This 3k up there goes from odd to even to odd, so the sign is alternating. And then the other thing is that the terms need to be decreasing and their limit needs to be 0, both of which are happening here. So that means that that one does converge, and its rationale is the alternating series test. Let's tackle that other one that looked like an alternating series. This one. And I say this looks like an alternating series because the denominator, plus -5 to the k, is either adding something larger than 3 to the k and positive, or larger than 3 to the k in magnitude and negative, which is turning it negative. So this denominator oscillates between positive and negative, but the important thing to note is that the two dominant terms are going to be 5 to the k in the numerator. That's the only term that's in the numerator, but eventually this -5 to the k is going to be much, much bigger, growing faster in magnitude, growing faster in terms of magnitude than the 3 to the k in the denominator. And so what we're really dealing with is something that behaves more like 5 to the k over -5 to the k, which does not have a limit of 0, right? That has a limit of 1. And in fact, because this is alternating, this is nearing plus or minus 1, depending on the sign at a particular k value. So this limit actually does not exist of the terms as k goes to infinity. So this fails the nth term test. If the limit of the terms is not 0, or you could say it passes the nth term test for divergence. How about that? If the limit of the terms is not 0, which in this case this limit does not exist because the magnitude of the terms is approaching 1 as k goes to infinity, and it's alternating in sign every consecutive k value. And so this right here is going to diverge, and that's going to be because of the nth term test. So that's worked for those two. Now we have to zoom in. We have our heavy hitters, so to speak. We have the asymptotic comparison test. We have the direct comparison test. We have a geometric series. We have the p-series option. And that's really what's left for us here. Now, looking at both of these, neither of them look like p-series, like saying this series is a p-series or this series is a geometric series. So already A and B are really not going to be on the table. What we're looking at is the direct comparison test and the asymptotic comparison test. Now, let's see what we're working with. It looks like really either one could work for us. Let's take a look at this guy. If we tried some direct comparison on it, we know that this is going to be term by term, square root of k cubed minus arctan k over k squared. That's going to be less than square root of k cubed over k squared. That reduces to 1 over k to the 1/2, or 1 over square root of k. Unfortunately, that doesn't do us much good at all because the series whose terms look like this diverges. So we've successfully said that this is less than something that diverges. Being less than something that diverges is not a conclusive inequality for us. Let's try the asymptotic comparison. The asymptotic comparison does the same thing. Note that as k goes to infinity, arctan k actually doesn't grow. It just approaches pi over 2. K cubed is the fastest growing term in the numerator there. And so the asymptotic comparison test, rather than the direct comparison test, will tell us that this right here, those terms are asymptotic to k cubed, square root of k cubed over k squared, which is equal to 1 over k to the 0.5. So it's asymptotic to the series whose terms look like this, which means they share behavior. So this series has the same convergence and divergence behavior as this series by the asymptotic comparison test, and we know that this is a p-series where p equals 1/2, which means it diverges. which means that our original series diverges as well. So this is going to be diverges, and that's by the asymptotic comparison test, which is D. And so we have to scroll down here because when we choose D, we actually have to provide a rationale. Note that we chose to compare to the series that was 1 over k to the 0.5. Direct comparison did not allow us, let's see if we can get there. There we go, k to the 0.5 power, or 1/2 power. A direct comparison test did not allow us to create an inequality that we could actually conclude something from. That leaves us basically with the direct comparison test to be used on that second series. We're sort of taking a deep breath and hoping that that's going to work out for us here. Let's take a look. Note that 2 plus sine k is going to be greater than k over the denominator and less than 3k over the denominator. We also note that the degree, k to the 5th plus k plus natural log of k, all under the square root, it looks like it has sort of the necessary beef in the degree in the denominator in order for this to go to 0 quick enough. So I'm going to zoom in on that k to the 5th as well. So the first thing that I'm going to do here in my sort of scratch work that I would do on my page is the following. Now, in order to conclude about the convergence or divergence of either of the series whose terms look like these guys that bound the terms in our series, we need to simplify that denominator a little further. So what if the denominator just was k to the 5th? That number would be smaller, which would mean that the full fraction with that number in the denominator would be bigger. Because we have a hunch that the denominator does go to 0 fast enough, unlike the last time. Oops, and let's take a look at that. That should say k to the 5th in there. Because we have a hunch that the denominator does go to 0 fast enough, let's take a look at this part of the inequality. Right? If we're wrong, we can always investigate this part of the inequality. That's fine too. By simplifying the denominator, we can actually create the following direct comparison. We know that the terms of this series are all less than or equal to the terms of this series, right? The denominator is smaller, the numerator is larger. And this can be simplified to 3 over k to the 3/2, which is a scalar multiple of a p series where p is equal to 3/2, and this converges. The series whose terms are all 3 over k to the 3/2 converges, and our series whose terms are all less than that is going to converge as well. Let's fill out the table above. That means that this converges, and that converges by the direct comparison test. And right here, we want to use the following inequality. Right? It is an inequality that relates the terms of series. And that's it. The key to all of these problems is doing ample scratch work on the side, allowing yourself to follow the logical conclusions of various ideas about these series. Like I said at the beginning, don't dwell too long on any single series. You shouldn't necessarily do these in order. Allow yourself to be attracted to the one that you can most easily deduce something about. For us, that started with here, and then we moved up to this one, and then we sort of had these two play off each other. Note that when we were working with these two, nothing seemed like a geometric series, nothing seemed like a p-series, and so we could do a process of elimination, saying, hey, this also isn't an alternating series, and the terms of this definitely go to 0 because the denominator is growing faster than the numerator. So that means that this is going to be one direct comparison and one asymptotic comparison. Be strategic. Be clear with yourself. And of course, show your work for your own benefit, right? There's no way that you can eyeball a lot of these. But of course, if there's a time crunch, might as well just sort of guess a little bit. There's no harm in that, but make them educated guesses. Pay attention to what you're doing and make sure that you provide these necessary justifications for each of the various tests. Number 3 involves one of those problems where we take a power series representation for a function that we know and we manipulate it for one that we're being asked for. So we need to write a power series representation for sine of x squared. So we need to start with our power series representation for sine of x. And then everywhere we see an x in this particular power series representation, we want to put an x squared. Let's simplify this a little algebraically and we'll get our final answer. It's also important to remember to read carefully for any requirements in how our answer should be formatted. Here we need the first three terms of the series and then the ellipse. And there is our final answer. One last note that we really want to be careful of is making sure that when we simplify this part algebraically, we want to distribute that x squared across the 2k plus 1 exponent to get us 4k plus 2 as the total simplified exponent on x when it comes to sigma notation. Let's also add in those indices and then we're done. You can always double check by plugging in k equals 0 to make sure that you get the required terms that you want, k equals 1, k equals 2. Part B of this asks us to write a series that represents the function g of x, where g's derivative is sine of x squared. So g is the antiderivative of the power series that we found above, and specifically we're told that g evaluated 0 is equal to 2. Let's take this one step at a time. First, we want to take the antiderivative of each term in the polynomial that we found in part A. Here is the general antiderivative for sine of x squared. Note that we have this constant c involved as the first term. We now want to use the fact that g evaluated 0 is equal to 2 in order to solve for c. Well, if we plug in 0 for x, we note that all of the terms involved in our series are going to go to 0. So if g evaluated at 0 is going to be equal to 2, that 2 depends on c entirely. Here I've written this out explicitly. Plugging in 0 for g, we see that all the terms involving x go to 0 and all that's left is c, and that has to equal 2. So c is equal to 2, and so our final answer here as far as what g, the antiderivative of sine of x squared, is equal to, so that when it's evaluated 0 is equal to 2, we now have this as our final answer. The final part of our problem asks us what interval is the representation that we found in B a valid representation of g, this antiderivative? And we recall that anti-differentiating, as in integrating or differentiating a power series representation, does not change the radius of convergence. And our original radius of convergence, when we started with sine of x, was valid for all x. The radius of convergence was infinite. And that did not change when we substituted in x squared up here. And so our radius of convergence was infinity, and so when we integrate, our radius is not going to change. This is still valid for all x, and so your answer should be that this is a valid representation for g for all x, and we know this because integrating does not change the radius of convergence, and our radius of convergence for sine of x squared was all x as well. Now, of course, we're not finished with this type of problem. Moving on to the next page, this is the gift that keeps on giving. We now have to use this antiderivative to write a finite sum that gives an approximation for the definite integral from 0 to 1/10 of sine of x squared dx that is within 1 over 10 to the 10th of the exact value. Well, the first thing we want to do is find the infinite series that gives us the definite integral's value there. And then we'll figure out exactly how many terms we need. Well, just like as if we were integrating a function, a regular function, we would take the antiderivative and evaluate it at 1/10, and take the antiderivative and evaluate it at 0. Now, a few things to note as we move from this line to this line. One is that yes, there is a constant 2 involved both in the evaluation of g at 1/10 and the evaluation of g at 0. But since we're subtracting g evaluated at 0 from g evaluated at 1/10, the constants will cancel. And so all we're left with are those terms that involved x. Now the terms that involved x, when you look at g evaluated at 0, they're all going to equal 0. So this entire thing is basically 2 minus 0. And this is 2 minus everything involved with 1/10. So the 2's are going to cancel in each part here. And everything else in here is 0. So what we're left with are the polynomial terms involved in g evaluated at 1/10. So here's what we have here. This is g with 1/10 plugged in for x, and we now need to see that this is an alternating series. And so a good error bound is the magnitude of the first unused term. We now need to figure out which term should be that first unused term. Which term is going to be less than 1 over 10 to the 10th? Well, we can take a look and just start with a guess. Maybe it'll be the second term. simplifying this out a little bit, what do we have? I've written out 7 times 3 factorial is 42 and 10 to the 7th there. Unfortunately, that's a far cry from 1 over 10 to the 10th, so that cannot be our first unused term. So let's try our third term as our first unused term, see what that size should be. Well, it is even smaller than 1 over 10 to the 10th, so that will be a satisfactory bound for us. So the third term is going to be our first unused term, which means that we only need to use 2 terms in order to get within the desired level of accuracy. An answer that involved the first 3 terms would have also been a valid answer, but note that an answer involving only the first term would not have had the desired level of accuracy. So your explanation as far as using this is an alternating series and using the magnitude of the first unused term as a bound for the error should be written out as part E. Part F encourages us to use the series representation of sine of x squared to compute the limit as x approaches 0 of sine of x squared minus x squared over x to the 6th. All we have to do is manipulate our power series representation to be equal to sine of x squared minus x squared over 6. We start with sine of x squared, and then we'll subtract off x squared. Important to note is that the first 2 terms here are going to cancel with each other. So really, all we have left is everything beyond that. Granted, that's an infinite series, but we'll see what's about to happen to it in a moment. The last thing that we need to do is we need to divide this by x to the 6th. The key thing to see here is that, again, in that first term, the x to the 6th is canceled and we'll be left with negative 1 over 3 factorial. The rest of these, the x to the 6th will cancel out of the denominator, but there will be an x to some power left in the numerator because all the powers are higher than 6 from the first term onwards in the numerator. So we always have something involving x in the numerator beyond the first term. And then as we take the limit as x approaches 0, this is now our chance here. Our limit as x approaches 0. Well, we have negative 1 over 3 factorial and everything else, because they have an x in the numerator, everything else is going to 0. And so we're left with negative 1 over 3 factorial. So that limit evaluates to negative 1/6. And that is our final answer. Moving right along to number 4, this is one of those fantastic problems that really tests your understanding of what it means for a series to converge, as well as your logical powers of deduction. Given particular pieces of information, what can you conclude definitely, and what do you not have enough information to say anything about? So here we're given a series. The terms are named a sub k, and the series is equal to 0.5, which means that this series converges. It's important right off the bat to say to yourself, okay, if a series converges, that means the limit of their partial sums exists and is finite. In fact, the limit of the partial sums is equal to 0.5. So that means the limit as n goes to infinity of s sub n is equal to 0.5. That's the definition of convergence. The limit of the partial sums exists and is finite. We're also told that all of the terms are positive, and we're given that s sub n is the nth partial sum, the sum of the first n terms, as we would suspect. Now the question to answer is which of the following statements must be true, which must be false, and for which is it impossible to decide given the information that we have at hand. We're told to justify our answers mathematically, and in each part we should cite an appropriate definition or convergence test or give examples which demonstrate that your answer must be correct. Our first one right off the bat is saying that the limit of the terms is 0.5. Now, is this true, false, or not enough info? Well, we're told that this series converges, which means that the limit of the terms must be 0, right? If the limit of the terms was equal to 0.5, that means that this series would diverge by the nth term test. So this is false. So that's what we have to say about that. The limit of the terms can't be 0. Otherwise, well, the series would diverge by the nth term test, and we're told up here that the series does not diverge. We're told that the series converges. All right, our next statement is that the series, where each term is not a term, the terms are made up of the partial sums. We're told that that converges. Well, from above, we're told that this series converges to 0.5. which means that the limit of the partial sums is equal to 0.5. And here we're creating a series out of those partial sums. So this series would look something like S1 plus S2 plus S3 plus S4 plus S5. And here we have an example where we have a series whose terms are not going to 0, right? We know by the fact that this series converges that the limit of the partial sums is going to be 0.5. And once we take those partial sums and turn them into the terms of a series, we now have a series whose terms do not go to 0. When we have a series whose terms do not go to 0, it diverges by the nth term test, and so this is going to be false. Now, let's take a look at C. We now have a series a sub k times cosine k. We're asked whether that converges or not. Well, cosine k is bound between positive 1 and negative 1. So even though the a sub k's are all positive, this series may not have all positive terms. Let's test it for absolute convergence. Now, if we take a look at the absolute value of the terms, we know that the absolute value of the terms is going to be bounded between 0 and a sub k. And that's true for all k. Well, since we know the series a sub k converges, that means the series of the absolute value of the terms a sub k cosine k also converges. This makes our series in question absolutely convergent. Does that mean that if we allow some of the terms to be negative, it will still converge? You bet. Absolute convergence is the strongest type of convergence for terms that have both positive and negative terms. Moving right along, let's take a look at D. Here we're asked if the series of a sub k to the fourth converges. Well, the series of the terms a sub k converges, which means that the limit of the terms has to be 0. And if the limit of the terms has to be 0 and the terms are all positive, that means eventually all the terms are less than 1 and they stay less than 1 for the remainder of the tail after some point. So far so good? Well, beyond this point, not only is a sub k less than 1, but a sub k to the fourth is going to be even less than a sub k. So for all k beyond that certain point, this is the relationship between a sub k to the fourth and a sub k, and so by the direct comparison test, since this series converges, this series will also converge. So this is going to be true. You would have to cite the direct comparison test here for full credit. Of course, I'm speaking rather than sort of writing out this exam like it was the actual thing. Let's take a look at E. We have 1 over k squared minus a sub k as the terms of our series, and we're told that that converges. No explanation needed. How nice. Okay, well, a sub k goes to 0, right? Those are the terms of our series that converges, so as k goes to infinity, a sub k goes to 0. So this denominator, k squared minus a sub k, is asymptotic to k squared. So that means that 1 over k squared minus a sub k behaves asymptotically similar to the series 1 over k squared. And 1 over k squared is a p series with p equal to 2, so it converges, which means that this converges as well. So that is true. All right, and last but not least, we have k squared times a sub k. This one is tricky. Here you just have to think for a little bit. We're told that the series whose terms are a sub k converges. You know, a sub k could be something like some scalar multiple of a p series, 1 over k squared. In which case, k squared times 1 over k squared would be equal to 1. And if every term in the series was 1, that would be a divergent series. However, a sub k could be some scalar multiple of a p series that's 1 over k to the fourth. In which case, k squared times 1 over k to the fourth is 1 over k squared, and so that's an example of it converging. So depending on what a sub k is equal to, this could potentially converge, right, if it's 1 over k to the fourth, or could diverge if it's 1 over k squared. So there are two possible examples that definitely change the convergence behavior. So unfortunately, there's not enough information to decide this one. This is a nice, quick geometric series problem. It says, before the semester starts, Ethan draws a chalk line 5 meters long across the blackboard. And on the first day of class, he erases the middle third of the line. So he has erased a distance of 5/3, leaving 2 shorter lines that are each themselves 5/3 in length. And then on the second day of class, he erases the middle third of each of the shorter lines, and then he proceeds to follow this pattern each day, erasing the middle third of every small line that remains. So here, he erases a third of 5/3 and another third of 5/3, so 2 times 5/3 squared. And then he erases a third of 5/3, and then he erases another third of 5/3, and then he erases another third of 5/3, and erases another third of 5/3. So that is 4, right, 2 squared times 5/3 cubed. And you can see that there's a pattern written over here, and that's intended for you to get an idea that this is a geometric sum. So after day 1, we have 5/3. After day 2, this is how much he's erased. After day 3, this is how much he's erased. So it says, write the geometric sum that gives the total length of line that Ethan has erased after day 122. Please write the sum in both ... notation and in sigma notation. Well, it's interesting to see that on day 2, the day number matches the exponent on the 3 in the denominator of the highest term, the greatest term, I should say, or the last term in the sum. And 1 fewer than that matches the exponent on 2. So let's take a look here. We want to write the geometric sum, so let's include the first 3 terms. Those are just going to be the same as the first 3 terms up here. And then we need to figure out what has been erased after day 122. Well, like I said, 2 is the coefficient, and it is raised to an exponent that is 1 less than the day's number. So if we're on day 122, that means that 2 needs to be raised to the 121st power. And then that's going to be multiplied by 5/3, and the 3 is going to be raised to the same number as the day. So that's going to be 5/3 to the 122nd power. And that's our answer for part A. Now, sigma notation, a little bit trickier. How do we figure this out? Well, we know that 2 is going to be raised to an exponent, and then 3 is going to be raised to an exponent that is 1 higher than the one that 2 is raised to. And we see that there is no 2 to begin with, so we know that k equals 0 is where we'll begin. And the final power that 2 is raised to is 121. And sure enough, that if we start at 0 and go to 121, that's a total of 122 terms, just as we'd expect. It now instructs us to write a closed form for the total length of line that Ethan has erased after day 122. We basically want to use that algebraic manipulation that we learned to compute the sum of geometric series. What we're going to do is we're going to write the partial sum, the 122nd partial sum, and then multiply it by the common ratio, and then take the difference of those two. So we have the 122nd partial sum here. We multiply by the common ratio, which is 2/3, and we see that this term is going to cancel with this term when we subtract the 2/3 times the 122nd partial sum off. This term cancels with this term. The first term that's missing, like right in here, the ... cancels with this term. This term is going to cancel with the first term that's missing here, and so all that we're left with is this term and this term. And all we have to do to solve for the 122nd partial sum is to divide by 1 minus 2/3, which is just 1/3. And dividing by 1/3 is really multiplying by 3. So what we have left is the following. And that is our final answer. It says, suppose Ethan keeps erasing every day indefinitely. What happens to the total length that he has erased? If it converges, to what does it converge? And if it diverges, how do you know? Well, that means that we are considering the entire infinite series, not just the 122nd partial sum. And this is a geometric series whose first term is 5/3 and whose common ratio is 2/3. So we want to use that a over 1 minus r formula to compute it. And we find that formula a over 1 minus r gives us 5. Does that surprise you at all? No, it really seems like Ethan is just erasing more and more and more of the line. And eventually, in the limit, he will be erasing the entire length of the line, which is an original length of 5 meters. It says that you may notice that as the days pass, he never erases the dots at the end of the intervals. And he started at the beginning. The first day he had 2 dots, Then the second day he had 1, 2, 3, 4, 5, 6 dots. The third day he had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 dots. And so what's interesting to note is that after day 1, he had 2 dots. Day 2 produced 4 more. Day 3 produced 8 more. And so the number of dots on a particular day is given by this series. And says, what happens to the number of these dots as Ethan keeps on with his routine? And of course, the number of dots goes to infinity. Crazy. Part E is just a fun question. It says the set of points that are still on the blackboard after infinitely many days of erasing is called the Cantor set. It's interesting, but it contains lots and lots of points. That's part D, but very little length. Part C. Is that cool? Circle 1, yes or no? Well, I'm a math teacher, so I'm going to circle yes. I hope you all do too. I think that was pretty cool. How nice. We are nearing the end. This is a nice, straightforward, find the interval of convergence of a given power series. So here we're given a power series that says find the interval of convergence of the power series. If the interval has endpoints, don't forget to check those too. Of course, in order to first find the radius of convergence, we need to use the ratio test. What do we look like and what is the result here? Well, we want to take the limit of the k plus 1th term over the kth term as k goes to infinity, and we want that limit to be less than 1. That's going to tell us our radius of convergence through the algebra that follows. There's a lot of algebraic simplification that has to happen. One is that we need to note that this exponent up here, this 2 times k plus 1, that's actually 2k plus 2 minus 1. So that's going to be 2k plus 1 in total. And so that will successfully cancel with the x plus 4 factor in the denominator, leaving just x plus 4 quantity squared in the numerator. Now we have a 9 raised to the k minus 1th power, and we have a 9 raised to the kth power down here. So the 1 in the numerator is going to cancel completely. We'll be left with just one factor of 9 down in the denominator. And then, of course, we have k to the 1/3 over k plus 1 to the 1/3. And the limit as k goes to infinity of k to the 1/3 over k plus 1 to the 1/3, that whole thing right here, the only part that actually involves k anymore, that's going to go to 1. So that second term here, that's just going to go to 1. What we're left with is that this limit is equal to x plus 4 quantity squared over 9. And according to the ratio test, we want this to be strictly less than 1 in order for this power series to converge. Doing a little bit of algebra, we see that x plus 4 has to be less than 3. And this is our moment right here. This tells us our radius of convergence, because this can be rewritten as x minus negative 4 is less than 3, which means the distance between x and negative 4 on the number line has to be less than 3. So we know our radius of convergence is 3. Our center is negative 4. So we now have at least the largest open interval of convergence is going to be 3 to the left of negative 4, which is negative 7, and then 3 to the right of negative 4, which is negative 1. We now need to test these endpoints, each of them separately, to see what happens. Let's test x equals negative 7 first. Here's the series that we get. Let's rewrite 9 to the k minus 1 as 3 squared to the k minus 1. Well, now we have a term that's negative 3 to the 2k minus 1 up in the numerator, and we have 3 to the 2k minus 2 down in the denominator. That leaves us with a negative 3. We have the negative 1 part is still to the 2k minus 1, but 3 is just all by itself. Now, upon close inspection, we want to double check what that exponent is that we're raising negative 1 to. 2 times k minus 1 is always going to be odd. So this is always going to be negative. It's not an alternating series. So this becomes negative 3 over k to the 1/3. Now this is a scalar multiple of a p series, where p is equal to 1/3. Unfortunately, that means that it's going to diverge. So we can't include negative 7 in our interval of convergence. Let's now test x equals negative 1. While plugging in negative 1 for x, we have the following series. I used the same algebra trick to express 9 to the k minus 1th power as 3 to the 2k minus 2th power. And so we end up with positive 3 over k to the 1/3 power this time. Again, a p-series, scalar multiple of a p-series where p equals 1/3, and so it diverges. We cannot include -1 either in our interval of convergence, and so that is our final answer. When doing a problem like this, make sure to show your work very clearly. Keep yourself organized so that it makes sense to you and to your grader. Of course, if there's a field at the bottom that asks you to fill this out, you absolutely should. And then this is always supposed to be a self-help thing. Most people just like check the box, check right next to that, but then they don't even go back to check if they actually did do the endpoints or not. But this is our attempt at trying to remind you of all the different pieces of this answer that need to be included in order to get full credit. We are so close to the end. We're still studying the same power series here, and it says, which of the following is a graph of f near the center of the power series? Please circle one. Well, the key to any problem like this where you're doing graph matching is that you want to write out a couple of the terms of this power series so that you can assess some information about the function value at the center, the first derivative at the center, and the second derivative at the center. Let's do it. This is really all the information I need to know. Because note, in this empty space right here, that's my information about a0, which is the function value at the center. Now remember, the center is -4. And if there's nothing before that leadoff term, x plus 4, that means that the function value at the center must be 0, which means that already we can eliminate D, we can eliminate C, and we can eliminate B. A, E, and F have a function value of 0 at -4, our center. Now we take a look at the coefficient on x plus 4 to the first, which is going to be 1. That means that a1, or the first derivative evaluated at the center, is 1. That means that we should see an increasing function at the center, and already E is the only one that does that. And we're done. In general, with these matching problems, what you want to do is write out the first at least 3 terms of the series so that you can figure out a0, a1, and a2. Remember, a0 is the function value at the center, a1 is going to be the first derivative at the center, and a2, which is 0 here, is the second derivative at the center divided by 2 factorial, but what you care about is its sign. Is it concave up? Is it concave down? And then matching accordingly. It asks us what the 25th derivative of f is evaluated at the center. And of course, we just need to figure out where x plus 4, what is the k value for when x plus 4 is raised to the 25th power. We can tell by looking at our equation for our terms that k has to equal 13 in order for x plus 4 to be raised to the 25th power. And so let's take a look at that term, because in that term, the coefficient on x plus 4 raised to the 25, that's going to be where we find information about the 25th derivative evaluated at the center. Will look something like this. And we can see the coefficient is actually all of that on that term. And that means that 1 over 9 to the 12th times 13 to the 1/3 power is equal to the 25th derivative evaluated at the center, all over 25 factorial. So if we were going to solve for that 25th derivative evaluated at the center, that would mean that it would be equal to 25 factorial over 9 to the 12th times 13 to the 1/3 power. A little bit of explanation talking about the recipe for the coefficients of a power series representation of a function. Of course, the power series representation of a function is its Taylor series representation as well. Not all power series are Taylor series, but all Taylor series are power series, and when you have a power series representation of a function, that is its Taylor series. So talking about how the information about the derivatives is encoded in the coefficients. So the information about the 25th derivative is going to be encoded in the coefficient for the 25th degree term. And then just using algebra from there on out would be a sufficient explanation. We are in the home stretch now. It says draw a clearly labeled picture and write a few sentences to explain how you know that the definite integral from 1 to n plus 1 of 1 over root x is less than or equal to the series from k equals 1 to n of 1 over root k. Well, that means drawing one of those graphs of the functions where you see the integral and then you draw on the rectangles whose areas all correspond to terms in the particular series. Let's do it. This light blue region here is the area that corresponds to this definite integral, and each of these red rectangles correspond to the terms in the series 1 over root k that start at 1, right? That's the function value at 1, width is 1. Function value at 2, width is 1. So the area of this first rectangle is equal to the first term in this series. The area of the second rectangle is equal to the second term in this sum, and it goes all the way to, this is the nth rectangle. And we can see that each of these rectangles, because 1 over root x is a decreasing function, this is a left-hand approximation, and so the sum of these rectangles is actually going to be greater than the shaded region, the actual area under the curve. It asks how many terms do we need to be sure that our sum is greater than 1,000, because we know it diverges to infinity. It just says be practical. We aren't looking for the very smallest number of terms, just a number that you're sure will work. And there are a bunch of different possible answers here, but one way to do it is to sort of write out a bunch of terms and see how they behave. We can see that these three terms here at the beginning are all going to be greater than or equal to 1/2. This one is exactly equal to, these are all greater than. Along the way to the next perfect square here, which is square root of 9, these are all going to be greater than or equal to 1/3. Up until 1 over root 16 here, all 7 in here are going to be greater than or equal to 1/4. And we can see that there's a pattern there. We know that there will be 9 more terms until the next perfect square, which would be 25, then 11 more to the next perfect square, which would be 36, then 13 more, which takes us to the next perfect square, which is 49, and it keeps on going like that. Now we can exploit this fact, and we can basically say, hey, the sum from k equals 1 to k equals n squared is going to be at least n. And so if we want to get a sum of at least 1,000, we'd need to go all the way up to 1,000 squared, which is equal to 10 to the 6th, which is 1,000,000 terms. I'm just going to repeat that once more. Note that the sum from k equals 1, down here, to k equals n squared, maybe here, is going to be at least n, just because of the relationship we've been dabbling with through here. So if the sum from k equals 1 to k equals n squared is at least n, that means that in order for us to get 1,000, we need to get 1,000 squared, which is about 10 to the 6th, which is about 1,000,000 terms. Again, that's just one way of approaching this. All different students used all different ways. But some of them used the improper integral. Some of them decided to use something more like this. As long as you explain your rationale, you will get some credit. And the clearer you are, you're usually going to end up with full credit. Best of luck on the exam. If you have any questions, please don't hesitate to ask.